Good day, grade 12 chemistry students. Today what we're learning about is energy changes and rates of reaction. What you're going to learn in today's video is some appropriate terminology to use in this unit, specifically referring to heat and enthalpy and a few other terms. You're going to learn how to write something called thermochemical equations, and we're going to learn how to solve problems involving heat using this equation here, Q equals mc delta T. Okay, so let's think about a question quickly here. What has more energy, a thimbleful of water at 200 degrees Celsius or a swimming pool at 20 degrees Celsius? Why? Let's think about this carefully. Write down your answer. If you chose the thimbleful of water, you're incorrect. Even though it's hotter, there's a lot less water. So when we refer to heat, we got to keep in mind that heat, which we're going to call Q today, is equal to the mass of something times the specific heat capacity, which we'll define later, times the temperature. So temperature and mass both play an impact on the amount of heat that's in something. So if we measured all the energy, okay, or heat energy or thermal energy, we're going to call it, in the ocean, for example, the ocean is massive. So it has a huge mass. The temperature might be cold. It actually contributes a lot of heat. So let's take our first term here, thermodynamics. This is the study of chemistry which studies energy and energy transfer. Now there's three forms of energy changes that we're going to talk to, energy changes or transfer that we're going to talk about. The first is chemical, which we refer to potential energy. This is energy in the bonds of molecules and substances, okay? Physical energy is kinetic energy, so that's the energy of movement. So that's really almost like, kind of like temperature, which we'll talk about, because temperature is the average, it's the measurement of kinetic energy. The one that we're not going to really focus on in this class is nuclear, which is potential energy. So there's energy inside the nucleus of an atom. And if you split that, you can release a ton amount of energy. Now, a couple terms here. Thermal energy is a form of kinetic energy or physical energy resulting from the motion of molecules. So when we talk about thermal energy, we're really talking about movement of molecules, and this is important. So an example is the acetylene torch releases a lot of thermal energy. It releases so much thermal energy that you can actually melt metal with it. So what is acetylene? It's C2H2. Now when we burn it, we react with oxygen and we make CO2 and water. There we go. Now, to balance this chemical equation, to describe thermal energy in this balanced chemical equation, we have to turn it into a thermochemical equation. Right now it's a skeleton equation, so let's balance it quickly. We have 2 carbons there, okay, on both sides, 2 hydrogens. I have 4 oxygens here, 5 plus the 1 from water, that's 5. So I'm going to put 5 halves here. I've now created a balanced chemical equation. If you wanted to get rid of that half, remember that you'd multiply everything by 2. Now the amount of heat released by this reaction, remember we can actually refer to this balanced chemical equation as either the amount of molecules, but we can also refer to this as the amount of moles. So I put a 1 there, and that means that I have 1 mole of acetylene that I'm burning here. Now in this question it says that I actually released 2,000 kilojoules, and this is a unit of energy, okay? So this is energy being released per 1 mole. So I released 2,000 kilojoules per every 1 mole. Now to make a thermochemical equation, I have to put this heat term as either a reactant or a product. Now I remember that an acetylene torch is hot, so that means that heat is exiting it, so that means I always make it as a product. So we're going to plug this term in as a product. Recall that it says 2,000 kilojoules per 1 mole, and we have 1 mole of acetylene. So all we have to do is we have to put an add at the end and put this as a product. This makes 2,000 kilojoules of energy. So now this term is now inserted into our equation, and we have a thermochemical equation. More specifically, it's a balanced thermochemical equation because we balanced it. So this is what a thermochemical equation is. It includes a heat term. Generally, it includes that heat term in something called kilojoules, which we'll explain what it means as we move further. So let's make another balanced chemical equation when we burn propane. What happens in your barbecue? Propane is C3H8. So if you burn it, react it with oxygen, makes CO2 and makes water. And what we're going to do is we're going to add a heat term here, and it's going to be in kilojoules. Now I'm going to add it on this side because heat is exiting. Now, how do I know heat is exiting? Because it's hot. And if it's hot, we call that special reaction, this special equation, an exothermic reaction, because heat is leaving. So let's balance this and let's see if we can make a thermochemical equation. So I've balanced it. I'm going to put a coefficient of 1 here. So it's still balanced. That means for every 1 mole of propane, I produce a certain amount of energy. Well, if we look at this term here means 2,220 kilojoules per 1 mole. So since I have 1 mole in my balanced chemical equation, all I have to do is go 2,220 kilojoules, because there's a 1 here. If there was a 2 here, I'd actually have to multiply this term by 2. We'll talk about that further as we go along. Now, really what's happening is, where is this energy coming from? It wasn't here in the reactant side, but it shows up in the product side. The question is why? Well, the answer is it came from change in chemical potential energy. What I mean is that these reactants actually have more chemical potential energy than these products do. But remember that energy, we're going to learn that energy cannot be created or destroyed. This is called the law of conservation of energy. So since energy cannot be created or destroyed, that means the energy on this reactant side has to equal the energy to the product side. So to make this equal, we have to include this energy term here. So let's think about this further. If we think about the potential energy in the system here, what ended up happening, and when we talk about the system, okay, what the system is the balanced chemical equation. So there was a change in potential energy between the reactants and the products. So the change in the potential energy of the system is actually turned into kinetic energy of the system, which is the product. So this heat here actually made these products vibrate very quickly, because remember, kinetic energy is the energy of movement. So these vibrated very quickly, okay? So the CO2 and water vibrated very quickly in your barbecue. And what happens is that energy gets transferred to other molecules that are around it. Now, this is the surroundings. Okay, so eventually over time, there was a change in potential energy compared to our reactants and products. The products were produced and started moving very quickly because the heat made them move very quickly. And that heat, the CO2 and H2O, would bounce into other molecules, which we'll call the surrounding. And that heat eventually gets transferred there. We're going to learn today that if we can measure the kinetic energy of the surroundings, we can determine the change in potential energy of the system. So in other words, the change in potential energy of the system is equal to the kinetic energy of the system, which is equal to the kinetic energy of the surroundings. So if we know this here, the kinetic energy of the surroundings, we can find the potential energy of the system. So next, what we're going to learn about is our chemical system, which I explained is the chemicals and the balanced chemical equation in the surroundings. Now I want you to know that we can only ever measure the surroundings. So we always ever just measure the surroundings. We can never directly measure the system. So we can only ever measure the surroundings, okay? The reason is that the surroundings are in a much greater quantity, but we know that the heat is either coming or going there. So when we talk about an endothermic reaction, what we're referring to is a cold reaction. It feels cold in the surroundings. And the reason why it's feeling cold is because there's a transfer of thermal energy from the surroundings into the chemical system, okay? There is a heat transfer here. So what ends up happening is that the heat ends up going into the chemical system, and there's actually more potential energy. So it's a little bit different than the reaction that we just discussed, which was an exothermic reaction where the heat left the chemical system. Here's an example of a chemical system balanced chemical equation, or thermochemical equation. So this is the equation here, and what we have is, if you've been paying attention, guys, you'll notice that this equation is the exact opposite of the previous equation. I just flipped the reactants and the products. Now this is endothermic because this energy is a reactant, okay? So whenever this is a reactant, that means energy is going into our chemical system. So we had some reactants with lower potential energy, and they were gaining energy from the surroundings. So surroundings, the heat is going into the chemical system, and you get products. That's not 50, that's 502s, and these guys have higher potential energy, okay? So what we notice is that since the energy is going into the system, what we measure is the surroundings, we notice that the heat is leaving and we have it feels cooler to us. Now we define heat as the transfer of thermal energy from a warm object to a cooler object. What we're noticing is that the reactants or the system is getting cooler, and so therefore the heat is leaving the surroundings and is going into the chemical system. This is an example of an exothermic reaction, which is the exact opposite of endothermic, where the chemical system is actually losing potential energy and releasing heat to the surroundings. Now, we always measure the surroundings, so what we notice is that exothermic reactions are always hot. So again, this is an exothermic reaction because potential energy is turned into kinetic energy of the system and eventually to heat that we can measure of the surroundings. So I'm going to quickly introduce a new term and we're going to come back over it again. But remember that there's a certain amount of potential energy in our reactants and there's a certain amount of potential energy in our products. Now this is chemical potential energy because it is in the bonds, okay? So there's a certain amount of potential energy here and there's a certain amount of potential energy over here. Now we can also call chemical potential energy another term, which we'll represent by the letter H. H is another word for enthalpy. Now, enthalpy is just another word for chemical potential energy, which we use the term H. Now, so we'll define that in a later video, but I'm just introducing this concept now. So the difference in potential energy, okay, the difference between these two values, we're actually going to learn it's actually the amount of heat that's released to the surroundings, okay? It's actually equal to Q, okay? So if we can somehow measure the difference in, if we can somehow measure the heat in our surroundings, released to our surroundings right here, if we can measure that, we actually know that it's actually equal to the amount of heat, or enthalpy change in our chemical system. Let me say that again because you're probably confused by that. That's okay, we'll cover it a couple times. The amount of heat released to the surroundings is actually equal to the difference in potential energy in our system. So if we can measure that, we know what's going on inside the chemical system. In order for us to determine what the enthalpy of a system is, okay, or to figure out how much heat was released from our chemical system, what we need is actually something called an ideal system. An ideal system can be imagined like a beaker, okay? And if I had a perfect beaker, that was insulated, and then I had a lid on it, so if I had my chemical reaction happening inside this beaker with this lid, no mass or energy, and no energy can escape. And if this occurs, I have what we call an ideal system. The reason why it's ideal is that if I can measure the heat in my surroundings, I know that it came from the system. And so therefore I know exactly, if I can measure that heat, I know that that was exactly came from my system. Now ideally, guys, in a lab, what we have is we actually have something called a closed system, okay? And a closed system means that no mass can escape, okay? But some energy can escape. Okay, so no mass can escape, but some energy can escape. And this means this is a closed system. This is not ideal because some of our energy is actually being released and that's impacting. It's a source of error in our calculations. And finally, an open system, which would just be a beaker, if you imagine a beaker without a lid at all, okay? And that means that mass and energy can escape from the chamber, and we have a difficult time making any sort of calculations. This is a special field called calorimetry, and we'll cover more in a field later, or in class later. Hope you enjoyed the video. That's it for now.